in some problems in physics, when we talk about forces, we're not actually given all the things that you think that you would need. So for example, you might not get the mass, but it turns out that a lot of these problems, if you solve them all the way through symbolically, you'll find that those values that you didn't have end up canceling anyway. So in this case, I want to walk through how you can solve a sliding to a stop problem, even if you don't know the mass of the object that is sliding to a stop. So in this particular example, we're going to talk about a hockey puck sliding to a stop 5 seconds after traveling 30 meters. If I start by drawing my free body diagram of what this scenario actually looks like, I get something that looks like this. Here I've got my hockey puck, and there is a force of gravity pulling that hockey puck straight down to the ground, and a normal reaction force, R, pointing straight up. And this hockey puck, as it's sliding to a stop on the ice, is only experiencing one horizontal force. There's a temptation to say that there's a force propelling it forward, but there really isn't. After it leaves the hockey stick or the skate, there isn't a force pushing it forward anymore. It doesn't have a rocket pack propelling it in that direction. Instead, the only force that's acting horizontally is the force of friction pushing it backward. So if I look at this free body diagram, there is a hidden equation here that's different than some of the equations that we use in our simple relationships in forces. And that equation becomes clear, I think, if you look at a different example. Let's say I had a free body diagram where I had 3 forces. A 7 Newton force going up, 7 Newton force going down, and a 4 Newton force going to the left. If I asked you what the net force was in this particular case, you would very quickly say, oh, the 7 and 7 cancel each other out. The net force is just 4. Now, the same thing is true here over on the left. We see that this hockey puck is only moving horizontally. So there is no net force in the vertical direction, which means that R and FG are equal and opposite to each other. They have to cancel each other out. And if they do, the only force that's remaining is this force of friction, just like 4 was the only force remaining in that simple example. So that I know that the net force in this case is equal to the force of friction. All right, from there, let's look back at the problem that we're actually trying to solve here. The problem that I'm looking for is, what is the coefficient of friction? Coefficient of friction is given by the symbol mu. It's that Greek letter. And the only equation that we've seen that symbol in is this one here. FF is equal to mu times R. All right. Now, we don't have the force of friction yet. We don't have R yet. But we do have enough relationships to help us get there. So remember, we don't actually have a mass in order to calculate Fg, but we know that Fg and R are equivalent, right? So R is equal to Fg. And we know that Fg is equal to mass times gravity. That's how you would calculate the force of gravity. We also, well, let's take that and see where that takes us. So if I were to substitute in these values to try to get us a little farther along, I know that R is really the same thing as Fg. So I can rewrite this and say FF is actually equal to mu times Fg. And to go a little farther, I can say, no, FF is equal to mu times mass times gravity. Now that is true on this left-hand side, or on the right-hand side here. And that takes us to a much simpler a value that's using these simpler values to it. I can also do the same sort of thing on the other side. I know that the force of friction is equal to the net force. And I know that the net force on an object is equal to the mass of the object times the acceleration of that object. So I can rewrite this. FF is really the same thing as net force. Mu times mg. And that net force is the same thing as mass times acceleration. Now, this equation gets me somewhere. I don't know the mass, but now I have a scenario where I've got mass on both sides, and it is the same mass. Mass times acceleration, that's the net force of friction of the puck, and mass times gravity, that is to find the weight of the puck. But mass cancels on both sides, so I'm left with acceleration is equal to mu times gravity. If I wanted to solve for mu, the coefficient of friction, that's just acceleration divided by gravity. But of course, I know gravity, I don't know acceleration of the puck yet, unless I look back on my problem. I know that the time is t, 5 seconds, the displacement, s, is 30 meters, and it comes to a stop. So that means that v is 0. So this is a SUVAT problem. I want to solve for acceleration. I know that s is 30 meters. I don't know u. I know that v is 0 meters per second. I don't know acceleration yet, and I know that t is 5 seconds. Normally, I would try to find acceleration right away, but you'll find if you try that, there isn't an equation that doesn't use u, so you feel like you're stuck. So first, let's actually solve for u, and then use that value to help us find the acceleration. So our equation to find u, in this case, is going to be s is equal to v plus u times t divided by 2. Plugging in what I know, I've got 30 is equal to 0 plus u times 5 divided by 2. 30 times 2 is 60 divided by 5 gives me u is equal to 12 meters per second. Now I have everything except for the acceleration, so I can find this acceleration using any equation that I want. I'm lazy, so I'm going to use the easiest equation I can see, and that's v is equal to u plus at. V is 0, u is 12, we don't know acceleration, and we know the time is 5. Negative 12 divided by 5 gives me an acceleration of negative 2.4 meters per second squared. Negative 2.4 meters per second squared just means it's opposing the motion, but opposing that positive velocity. In this case, in forces, we can just treat that as a magnitude. That will be just fine because we know that the direction is associated with the arrows that we have up here. So now we have an acceleration. That's how fast the hockey puck is slowing down. And that is enough now to plug in and solve for mu. Mu is simply equal to 2.4 divided by 9.81. 2.4 divided by 9.81 is 0.245. Mu, the coefficient of friction, is a unitless number. So as a reminder, to get to that 0.245, where we started was we used our free body diagram to help us take this equation and give us more information. So instead of FF, we were able to convert that into the net force because FF is the only force that remains after things cancel. Then that net force is equal to mass times acceleration. So on the left side, we were able to turn that to MA. On the right-hand side, mu times R, we know that R is always equal to the force of gravity, and the force of gravity in this case is equal to mass times gravity. So we were able to plug in mg instead of R, and then ultimately cancel out m, solve for the acceleration with this equation, then found 2.45.